Today we're going to be doing our last of our transformations. We've done translations, which was sliding. We've done reflections, which was flipping. And we've done rotations, which was spinning. And the last thing that you can do to change a shape is to do a dilation. And so that's what we're going to talk about today. For a dilation, translation, rotation, and reflection all changed the position of a shape. So we changed where it was, while the size and the shape remained exactly the same. The fourth transformation that we are going to discuss is called a dilation. And a dilation changes the size of the shape without changing the shape itself. But we are changing the size of it. So unlike translation and reflection and rotation, where everything about the shape stayed the same, its size and its shape stayed the same, we just changed where it was on the piece of paper. The dilation does actually change its size. Usually you hear this word a lot when you go to the eye doctor. They dilate your pupils because your pupils can open up and get very big to let in a lot of light, and then they close and get really, really tiny when it's really bright outside and it doesn't let in as much light. And that's because your pupil is still staying a circle, but it's getting bigger or it's getting smaller, so it's changing its size. When you enlarge a photograph or you use a copy machine to reduce a map, you are making dilations. Enlarge means to make a shape bigger. Reduce means to make a shape smaller. The scale factor tells you how much something is enlarged or reduced. How much bigger are you making it, or how much smaller are you making it? Notice, each time the shape transforms, the shape stays the same and only the size changes. So this is a 200% enlargement, so it's twice as big. This is a 50% reduction, so it's half the size. All right, look at the pictures below. Dilate the image with a scale factor of 75%. So it is smaller, because that's less than 100. 100% would keep me exactly the same. So 75% is 3/4 the size of this one. All right, 150%. So that's more than 100. So that means that it's getting bigger. And so that shape got bigger by about half. Now, 100% stays exactly the same. So why is a dilation of 75% smaller, a dilation of 150 bigger, and a dilation of 100% the same? Just like we said before, 100%, that's the whole shape. 75%, it's only 3/4 of the shape. And 150% is, more than the whole shape itself. When you think about percentages, 100% is the whole. If we think about fractions, things that are bigger than 1, that's more than the whole. Things that are less than 1, that's smaller than the whole. So this is why they end up being smaller. Now, rules. As always, we've been talking about all of these things with respect to the coordinate plane. When we talk about dilations with respect to the coordinate plane, we are generally talking about dilations with respect to the origin. And so our rule for the points when we are doing this with respect to the origin, when we're dilating it with respect to the origin, is that we just have to take the scale factor and multiply the point. We multiply the x-coordinate and we multiply the y-coordinate, and that will give us a dilation with respect to the origin. So it's pretty straightforward. If we look at some examples, we have the trapezoid EFGH. Find the coordinates of the dilated trapezoid if EFGH has a scale factor of 2. So scale factor is how much bigger is it getting. And notice this number is bigger than 1. Again, we talked about 1 is the whole. So if it's bigger than 1, it's getting bigger. If it's less than 1, it's less than the whole. It's getting smaller. So this shape must be getting bigger, and we're dilating it by a factor of 2. So that just means that we need to multiply everything by 2. So E prime is going to be -2 for. F prime would be for 2. G prime would be for -2. And H prime would be -2, -4. Because we had to take everything, didn't switch anything, didn't change any signs. We just multiply it by the scale factor. So multiply each of the coordinates by 2. And there's all of the lovely points that we would get. So let's see what that would look like on the graph. So graph the original. There's E, F, G, H. So that was the original shape. And then when we multiplied everything by 2, these were the points that we got. So notice that we were reflecting it with respect to 0, 0. So the distance this point was from the origin got twice as big. The distance that this point was from the origin got twice as big. The distance that this point was from the origin got twice as big. And the distance from the origin got twice as big. So it's with respect to the origin that we are dilating these. Now, here's our trapezoid. Find the coordinates of the dilated trapezoid if the scale factor is 1/2. So that's less than 1. So with that being less than 1, that tells me that my shape is getting smaller. The scale factor is less than 1, so my shape is getting smaller. But the rule doesn't change. I'm going to multiply everything by 1/2. So this would be -2, and then this would be 7/2, or 3.5. F prime, half of that would be 1. Half of that would be 3.5 again. G prime, 0. Half of 0 is still 0. 0 is a very boring number when it comes to dilations. Half of 4 would be 2. H prime, we'd get -1 and 2. So we just take half of everything because our scale factor is 1/2. So those would be our points. Now you can leave them as fractions, or you can do the decimal. It is important to kind of pay attention to the directions. Generally in algebra, we like to have exact numbers. We like the fractions. But if you're graphing it on a coordinate plane, fractions aren't as useful as decimals. So it's good to kind of do both. Here was our original shape here in yellow. And then after we graph the new ones, again, knowing that it's 3.5, you just kind of go halfway on the coordinate plane. But notice that it is half the size of the original. So let's try to make sense of all of this. Transformations. If you're changing the position of the shape versus changing the size of the shape, right? If you're changing the position of the shape, it's either a translation, meaning we slid it somewhere, a rotation, we spun it, we turn it around, or a reflection, we flipped it. If we're changing the size of the shape, then we know it's a dilation. But these are all the ways that you can change and move a shape in a picture. See if you can identify the transformations that created the new shape. What happened to this shape? It's the same shape and it's the same size, so it's not a dilation. It's still facing the same direction, so it's not a reflection, and more than likely not a rotation, so it must be a translation. It just slid over and down. All right, now this one changed size, automatically a dilation. Ooh, now this one, it didn't change shape or size, so it's not a dilation. It is facing another direction, so it's either going to be a rotation or a reflection. So we have to decide which one it is. And if it's a mirror image, then it might be a reflection, but it seems to be sticking to this point, so I think it's a rotation. All right, can I identify the transformation in this picture? Notice there's this horizon line here, and everything is reflecting in the water. That is a reflection. And then in this picture, what do we notice is going on? Well, I do notice that the helicopter things are spinning, so that's going to be a rotation. Ooh, what's going on in this picture? The cars are moving. So they're moving from one place to another, so that's going to be a translation. Oh, and then the pupil in the eye getting smaller and bigger, that is a dilation. So these things show up in the real world too. It's how things move and how things are. Ooh, now this shape appears to have that symmetry that we were looking at right down the middle. If we split it down the middle, this building is the same on either side. So that's a reflection, and in particular, reflectional symmetry.